In the last lecture, we talked about how we could call Gurobi within Python. In particular, we could create a linear program, solve a linear program, and get the optimal solution to this linear program by calling Gurobi all within Python without getting out of Python at all. In the example that we looked at in the last lecture, we had a small linear program. We had two decision variables in our linear program and two constraints. So in that sense, it was relatively comfortable to create each one of the decision variables and each one of the constraints one by one manually. So that was the example that we looked at in the last lecture. In today's lecture, we're going to continue with calling Gurobi within Python, but now we're going to look at an example that's going to have significantly more decision variables than significantly more constraints. So in that sense, it won't be comfortable to create each one of the decision variables and each one of the constraints manually one by one by one. So in this lecture, we're going to look at an example for calling Gurobi within Python, where we're going to be constructing all of the decision variables and all of the constraints through loops. Okay, so we're going to be looking at an example today for calling Gurobi within Python, where we have to construct all of our decision variables and constraints through loops. Good. In particular today, we're going to solve an assignment problem. So let's say we have an assignment problem where we have 3 technicians and 3 jobs. And in this table, we're giving the reward from assigning a particular technician to a particular job. Namely, if I assign technician 2, for example, to job 3, we make a reward of 8. If you assign technician 1 to job 1, we make a reward of 2. If you assign technician 3 to job 1, we make a reward of 8, and so on and so forth. Each technician can do at most 1 job. Each job needs 1 technician. Well, we want to figure out which technicians to be assigned to which job so that we maximize the total reward from the assignments. Okay, so this is the problem that we're going to solve by calling Gurobi within Python. Okay, so let's remind ourselves what the compact formulation of the assignment problem looks like. So let me draw the network over here. So we have a bunch of text here. We have 3 texts here, and we have a bunch of jobs on the other side of the network. So we can assign technician 1 to job 1. We can assign technician 1 to job 2. We can assign technician 1 to job 3, technician 2 to job 1, technician 2 to job 2, technician 2 to job 3, technician 3 to job 1, technician 3 to job 2, technician 3 to job 3. Okay, great. So then to model the assignment problem as a mean cost network flow problem, a few lectures ago, what we did was we put a supply of 1 to each one of the technician jobs, and we put a demand of 1 to each one of the, we put a supply of 1 to each one of the technician nodes, and we put a demand of 1 to each one of the job nodes, and we wanted to figure out how to send the supplies from the technician nodes to satisfy the demand at the job nodes so that the total reward from the flows is going to be as large as possible. So that's one way to look at the assignment problem. So now let's write down the compact formulation of the assignment problem, because that compact formulation is going to be essentially what we will be putting into Gurobi, what we will be putting into Gurobi through Python. So what is the data for our assignment problem? Let's say n is the number of technicians or number of jobs. They're equal to each other. Good. And what other data do we need? We also need the reward from assigning a certain technician to a certain job. So let's say for that piece of data, we use Rij, reward from assigning Xi to job j. Okay, so this is all the data for the assignment problem. Number of technicians or the number of jobs, which is equal to each other. And Rij is the reward from assigning technician I to job j. Let's think about the decision variables. We're going to denote our decision variable as xij, and xij is going to be the flow from technician I node to job j node. And if there is flow from technician I node to job j node, then we're assigning technician I to job j. Our decision variable is xij, flow from technician I to job j node, flow from tech I to job j, meaning that if I have flow from tech I to job j, I'm assigning tech I to job j. Okay, good. So now let's write down the compact formulation of the assignment problem. We want to maximize the reward from technician to job assignments. If there's a flow from technician I to job J, then Xij is going to take value 1. If there's a flow from technician I to job J, then Xij is going to be 1. And if there's a flow of from technician I to job J, then we're going to make a reward of Rij. Let's add over all possible technicians I, there's n of them, and all possible jobs J, and there is also n of them. So this is the reward from all of the assignment decisions. Great. So now let's write our constraints. The first constraint we would like to write down is, each technician I is going to get exactly one job. Each technician I is going to get exactly one job. We're going to write a constraint that says each technician I is going to get exactly one job. So we would like to write a constraint that says something like this. Let's say something like this. Technician I can go to job 1. This is the flow from technician I to job 1. Technician I could go to job 2. Technician I could go to job 3. So this is the total number of jobs that technician I is getting. Technician I could go to job 1, flow from technician I to job 1. Technician I could go to job 2, flow from technician I to job 2. Technician I could go to job 3, flow from technician I to job 3. So this is the total number of jobs that technician I is getting. That should be equal to 1, meaning that technician I should be getting exactly one job. So let's write this constraint in more compact form. xi1 plus xi2 plus xi3, meaning that xij's added over all j's has to be equal to 1. And we have this constraint. This says that technician I is going to get exactly one job. And we have this constraint for every technician I from 1 to n. So this is the constraint that says each technician I is going to get exactly one job. We have one of these constraints for each technician I. And likewise, we're going to write another constraint that says each job J is going to get exactly one technician. Each job J is going to get exactly one technician. Each job J is going to get exactly one technician. So to write a constraint that looks like this, job J, there could be a flow from technician 1 to job J. There could be a flow from technician 2 to job J. There could be a flow from technician 3 to job J. There could be a flow from technician 1 to job J, technician 2 to job J, technician 3 to job J. So this is the total flow into technician J. There could be a flow from technician 1 to job J. This is the flow from technician 2 to job J. This is the flow from technician 3 to job J. So this is the total flow into job J. Okay. This is the total flow into job J from all of the technicians. So this is the total number of technicians that job J is getting. This should be equal to 1. Okay. There could be a flow from technician 1 to job J, a flow from technician to job J, technician 3 to job J. So this is the total number of technicians that job J is getting. So the total number of technicians job J is getting should be equal to 1. So now x1j, x2j, x3j all added all up. So this is going to be xij's added over all i's has to be equal to 1. And we have this constraint for every job J, ensuring that each job J is getting exactly one technician. And lastly, our decision variables are non-negative. Good. So this is the compact formulation of our assignment problem. So now we're going to take this assignment problem and put it into Python. And we're going to solve this assignment problem by calling Gurobi within Python. Good. So let me go to my PyCharm and start writing my code. We already have some of the code prepared here. So some variables I already created in our Python code. I have a variable in my Python code that's keeping track of the number of technicians. And I have a Python variable in my code that is keeping track of the number of jobs. And of course, the number of jobs and number of technicians are equal to each other. But we use two different variables here in our Python code here, just so that it's going to be clearer when we're loop holding over technicians and when we're loop holding over jobs. Okay, so that's why we use two different variables here, number of technicians and number of jobs. It's going to be clearer when we loop over jobs and when we loop over technicians. And the other variable that we already defined in our Python code is this rewards matrix, two-dimensional rewards matrix. And this two-dimensional rewards matrix is going to keep track of these Rij values, reward from assigning technician I to job J. And we already initialized this two-dimensional reward matrix. And this two-dimensional reward matrix is initialized to capture the rewards that we already looked at on the previous on the paper page. Let me say it that way. And here are those rewards on paper. Reward from assigning technician 1 to job 1 is $2. Technician 1 to job 1 reward is $2. Technician 1 to job 2 is $4. Technician 1 to job 3 is $5. And then we have 3, 6, 8, and then 8, 4, 9. And of course, we're indexing the technicians and jobs starting from 1 over on this page. But in our Python code, the technician and the jobs are going to be indexed starting from 0 to 2. That's how Python is indexing the arrays, obviously. Good. So now we have all the data for our problem, number of technicians, number of jobs, and our IJs, reward from technician I to assigning from technician I to job J. So now let's start creating our linear program. We know that at this point, this subroutine model is creating an empty linear program. So let's create an empty linear program. We can also give an example to our linear program. Let's call our linear program assignment example. And then that empty linear program that we created, let's put that in a variable in Python called my model. So now this my model in Python, my model variable in Python is pointing to an empty linear program that we just created. And as we go along, we're learning Python comments that allow us to interact with Gurobi. So let's write those Python comments on this page as we go along. So now we learn the model command. What the model command is doing is it's just creating an empty linear program. Good. So next thing we're going to do is we're going to create the decision variables. What are our decision variables? What are our decision variables? Our decision variables are xij's. For every technician I and job J pair, we have a decision variable xij. So let's create those decision variables. Let's loop over every technician. And let's loop over every jobs. So now for each ij pair, I'm going to create and add a decision variable into my linear program. My model.addVar. We're going to add a decision variable into our model for every ij pair. So into my model, add a decision variable. The type of this variable type is a continuous variable. We're solving a linear program, so our decision variables take continuous values. And let's also give a name to our decision variable. So let's call the name of our decision variable as x underscore. And to that, add the identity of the technician and add the identity of job J. So name of our decision variables are x underscore ij, and I is the identity of the technician, j is the identity of jobs. Good. So in this loop, I'm creating one decision variable for each for each technician I, and for each job j, and I'm adding them to my linear program. Good. But now, as I create and this is important, this is important now, but now, as I create the objective function and the constraints in my linear program, I want to be able to refer to these decision variables. I created all of these decision variables xij's and put them in my linear programming model. But now later on, when I'm creating my objective function and constraints, I need to be able to refer to these decision variables. So what we're going to do is we're going to create a two-dimensional array, call that two-dimensional array, x variables array. And as we create these decision variables, we're going to add these decision variables into that two-dimensional array. And later on, when we're creating our objective function and constraints, we're going to be able to access those decision variables through that two-dimensional array. Okay. So now here's what we're going to do. We're going to create a two-dimensional array. We're going to create a two-dimensional array. Okay. Let's call this array, if you like, xVars array. And this dimension is going to be the number of texts, sorry. I is the number of texts. And this dimension is going to be the number of jobs here. Good. And the ijth entry of this array is going to point to the decision variable xij. Okay, good. So we're going to create a two-dimensional array xvars. And this dimension of this array is going to have number of text component, and this dimension of 3 is going to have number of jobs component. And the ij component of this array is going to point to the decision variable xij that we created. So let's implement this idea in our Python code. So let's create an empty two-dimensional array. Let's call it xvars array. So I created my rows, and I'm going to create it for each. I create my columns, so I'm going to create my rows. Range, number of texts. So we created our two-dimensional array, number of technicians by number of jobs, number of technicians by number of jobs. So then whenever we add a decision variable into our model, we know that add var gives us a reference to the variable that we just created. So then the x vars ij10 is going to be now the variable that we just created. Okay. So whenever we say my model.add var, we add a variable into our linear programming model, and this returns a reference to the decision variable that we just added and created and added. So now x vars ij10 is now pointing to that decision variable that we just created and added into our model. Good. And we know that after we create all of our decision variables, we call my model.update to ensure that all of our decision variables are properly registered. So now let's make a list of all these cool comments that we learned. So my model creates an empty linear program. So then we learned if I get a Gurobi model and say add var subroutine adds a decision variable into a model. And then we also learned Gurobi model.update. This ensures that all the decision variables that we created are properly registered into our linear programming model. Good. The next thing we're going to do is we're going to create our objective function. To create our objective function, we're going to create first an empty linear expression. And we know that a linear expression is created by the function lineexpr. So let's say objective expression is given by an empty linear expression. What is our objective function in our assignment model? We look at all the decision variables xij's, multiply them by rij's, add it all up, right? So we look at every ij pair, we take the decision variable xij, multiply it by rij, add it all up in the objective function. So let's create this objective function. Let's again loop over every technician I, or I in range number of technicians. Let's loop over every job j. Good. So now into this linear expression, into this linear function objective expression, we're going to add rij times xij. Rij is included in the reward arrays ij10 and xij is included in the x vars arrays ij10. Good. So this is what's cool and useful about creating this x vars array. When I created and added my decision variables into my linear program, this x vars arrays have been filled in. This x vars array has been filled in by the decision variables that I created and added into my linear program. And whenever I'm writing up my objective function, I access my decision variables through the x vars array. Good. So now we created the objective expression. We created the linear function that keeps track of our objective function. So then we go to our linear programming model and we set the objective function of our linear programming model as set objective as this linear function that we created. And we also tell Gurobi that we're going to maximize our objective function. Okay, good. So now let's make a note of all the functions that we use. A linear expression creates an empty linear function. Okay, and then a linear programming model dot set objective sets the objective function of that linear programming model. Here. So then lineexpr creates an empty linear function. And also if we go to a Gurobi model and then we set objective. This sets the objective function of our linear program. So now we created the objective function of our linear program. We're going to think about constructing the constraints in our model. To construct the constraints in our model, let's look at the compact formulation of the assignment problem. Here's the compact formulation of the assignment problem. In the compact formulation of the assignment problem, for each technician I, we have a constraint. In the compact formulation of the assignment problem, for each technician I, we have one constraint. And in the constraint corresponding to technician I, for each I, we're taking the sum of the xij's or the overall j's and setting it equal to 1. Okay, so for each technician I, we're going to have a separate constraint, and the constraint corresponding to technician I, we're going to sum up xij's overall j's and set it equal to 1. So those are the constraints that we're going to write. Let's go back to our code. So for each technician I, we're going to write a constraint for I in range, number of techs. So now I'm writing the constraint corresponding to technician I. For each technician I, I'm going to write a constraint. So now let's create an empty linear function that is going to keep track of the left-hand side of the constraint for technician I. Let's create an empty linear function that's going to keep track of the left-hand side of the constraint for technician I. Let's call it constraint expression. That's an empty linear expression. Good. So now we're writing the constraint for technician I. What are we going to do? Take the xij's, add it over all j's. Take xij's, add it over all j's. So loop over all j's and add all the xij's. Take the xij's, add it over all j's. Okay. So when we're writing the constraint for technician I, the left-hand side of the constraint is sum all the xij's, add it over all j's. Or j in range, number of jobs. Okay. Then our constraint expression is going to be 1 times x vars, ij entry. So now, once we get out of this loop inside, we created the left-hand side of the constraint corresponding to technician I. Once we get out of this loop, we created the left-hand side of the constraint corresponding to technician I. We created the left-hand side of this constraint corresponding to technician I. So now let's add this constraint into our linear programming model. My model dot add constraint. Okay. Add constraint. Left-hand side of the constraint is the left-hand side of the constraint is just this linear function that we created. The sense of this constraint, the sign of this constraint is inequality, and the right-hand side of this constraint is a 1. So we're adding the constraint. The left-hand side is just the constraint expression that we created. The sense of this constraint is equality, and the right-hand side of this constraint is 1. And let's also give a name to this constraint. This is a technician constraint. This is the constraint that technician I gets 1 job. So this is a constraint that technician I gets 1 job. So text underscore, let's take the identity of the technician here. Good. So now we added the constraint for each technician I, saying that each technician I is going to get exactly 1 job. Let's go to our compact formulation of the SLMO problem. So now we took care of these constraints. So now we're going to take care of these constraints. What are we going to do? For each job J, we're going to write a constraint that says each job J is going to get 1 technician. For each job J, we're going to write 1 constraint. And we're going to write a constraint that says each job J is going to get 1 technician. So now for the constraint for job J, what we're going to do is, when we're writing the constraint for job J, we're going to take all the xij variables, add them over all i's. Okay. So when we're writing the constraint for job J, we're going to take all the xij variables, add them over all i's. So then we're going to write a constraint for each job J. Good. So now let's create an empty linear expression. Good. So now I'm writing the constraint for job J. When I'm writing the constraint for job J, I'm going to take all the xij variables, add them over all i's. So let's loop over all i's. And then into that empty linear function that we created over here, we're going to add 1 times the x vars I j. So when we're writing the constraint for job J, we're taking all the xij variables, adding them over all i's. Okay. So once we get out of this inside loop, we created the left-hand side of the constraint for job J. Once we get out of this loop, we create the left-hand side of the constraint for job J. We created this thing. Now I'm going to add the constraint where the left-hand side of the constraint for job J is this linear function that we created. The sense of the constraint is equality. The right-hand side of the constraint is 1. My model dot add constraint. The left-hand side of the constraint is this constraint expression that we created. The sense of the constraint is equality constraint. And the right-hand side of the constraint is 1. And let's give a name to this constraint. This is a constraint that says every job J is going to get 1 technician. So I'm going to call this as a job constraint. This is a job constraint for job J. Good. So now let's try to make a list of everything that we learned. Linear expression creates an empty linear function. We know this before. But now if I go to a linear programming model and said add constraint, that is going to add constraints into our linear programming model. Back here. So linear expression creates an empty linear function. But when we go to a Gurobi model and say add constraint, that's going to add a constraint into our Gurobi model. Great. So let's go to our Python code. After we create all of our objective function and constraints and everything, we also need to call myModel.update to make sure that our objective function and constraints are properly registered. Again, as we talked about in the last lecture, we need to call this update function at least twice. Once after we create all of the decision variables, and once after we create the objective function and all of the constraints. Okay, we need to call update at least twice, once after we create all the decision variables, and once after we create the objective function and all of the constraints. You can call update as much as you want, but these are the minimum number of times that we need to be calling update. So then, presumably, we created all of our decision variables. We created our objective function. We created constraints that says each technician I gets 1 job. And we created this constraint that says each job J gets 1 technician. So this creates all of the linear program. Let's make sure that our linear program has been created correctly. Let's write our linear program into a text file. Let's see what it looks like. MyModel.write. Let's write our linear program into a text file. Let's say the name of the file is going to be assignment example. And let's give an extension LP here just so that Gurobi and Python understands that we're going to dump our linear program into a text file in LP format. Once we run this code, if I didn't make any mistake, in this directory structure, we should have a text file, assignment example.lp, that is including the linear program that we constructed. Okay, assignment example LP, let's run this code, run assignment example.lp. Okay, now in the directory structure, we have this text file, assignment example.lp. Let's look at what that linear program looks like. Okay, we have a decision variables x0, x00, x01, x02, x10, x11, x12, x020, 21, 22. So technician 0 going to job 0, technician 0 going to job 1, technician 0 going to job 2, so on and so forth. Technician 2 going to job 0, technician 2 going to job 1, technician 2 going to job 2, so on and so forth. And let's look at the values of these objective function coefficients. 2, 4, 5, 3, 6, 8. 2, 4, 5, 3, 6, 8, and 8, 4, 9. The objective function seems to be doing perfectly fine. Let's look at these tech constraints. That's saying that each tech is going to take exactly 1 job. Let's get this one, the constraint for tech 1. Tech 1 could go to job 0, tech 1 could go to job 1, tech 1 could go to job 2. So this is the total number of jobs tech 1 is going to. That should be equal to 1. So technician 1 is going to exactly 1 job. Okay. And here are my constraints that is saying that each job is going to take 1 technician. Let's look at the constraint for job 2. Technician 0 could go to job 2, technician 1 could go to job 2, technician 2 could go to job 2. So this is the total number of technicians that job 2 is getting. Technician 0 could go to job 2, technician 1 could go to job 2, technician 2 could go to job 2. So this is the total number of technicians job 2 is getting. So that should be equal to 1. So these constraints are saying indeed that each job is going to get 1 technician. So we constructed our linear program indeed in the correct way. Our linear program is correct. So whenever we create a linear program in Python, it's always good to write the linear program into text file and visually inspect it just so that, whatever we did in code is creating exactly the linear program that we would like to create. Okay, so whenever we create a linear program in Python, it's good to print that linear program into a text file. It's good to dump that linear program into a text file so that we can visually inspect that text file to make sure that we created the linear program in the way that we wanted it to. So now we learned another comment, a Gurobi model.write, dumping the model into a text file. So then let's write that one, Gurobi model dot write, that is dumping the model into a text file. Good. So now let's solve our optimization model, my model dot optimize. And let's run our code and let's see what happens when we optimize our model, when we solve our model. Let's go to assignment example.py. Let's run our assignment example. Okay. We cranked up the simplex through the Gurobi optimizer. After a few iterations, we get the optimal solution. The optimal objective value is 2 times 10 to the 1, so the optimal objective value is 20. And the next thing we want to do is we want to look at the values of the decision variables in the optimal solution. The next thing we want to do is we want to look at the values of the decision variables. And we also presumably want to maybe look at maybe want to grab the optimal objective value. Let's first grab the optimal objective value. How do we grab the optimal objective value? If you go to a linear programming model, my model, and look at the field objective value, this returns the objective value of your linear programming model. So let's assign it to a Python variable, objective value. Okay. So then we learned 2 new things, we have 2 more new functions here. One is optimize. And if you go to a Gurobi model, linear programming model, and say objective value, that field is returning the objective value of our model. Let's make a note of those. Gurobi model.optimize solves a linear programming model. Good. And let me write the remaining ones over here on this corner, and let me write them in red so that it's not going to create too much confusion. And what else did we learn? What else did we see? If you take a Gurobi model, linear programming model, and look at the obj_val field, that's going to return the corresponding objective value of the model that you have. The next thing we're going to do is naturally we're going to look at the optimal values of our decision variables. We're going to look at the optimal values of our decision variables. Okay. Well, now that we got this optimal objective value, let's print that optimal objective value just so that we have that in front of our face. So optimal objective value is good. So now let's print the solution, the optimal solution to our model. Let's print the optimal solution to our model. If you take a linear programming model and say get vars, run the get vars subroutine, this returns a single dimensional array that includes all of the decision variables in our model. Okay. So if you go to a linear programming model, if you take a linear programming model and say dot get vars, it returns a single dimensional array that includes all the decision variables in our model. So let's call that single dimensional array all vars. Let's now iterate over the elements of this array. Or let's say current var in all vars. So now this current variable iterate is iterating over all the variables in our model. Then let's print the name of the variable and the value of the variable. So let's take when I have a Gurobi variable, so now this current variable is looping over all the variables in our model, all the decision variables in our model. So this current variable, current var, is looping over all the variables in our model. Now for all of my variables, I'm going to print the name of the variable and the value of this variable. And in a Gurobi decision variable, there are 2 fields. Var name returns the name of the variable. And if you have a Gurobi variable and the other field, x returns the value of that variable. And let's turn that value into a string so that we can print that properly. So now what we're going to do over here is that we're going to loop over all the decision variables in our model, print their names, and print their values. So let's say the optimal solution is, okay, good. To repeat what we did over here is that, again, when we have a linear programming model and say get vars, it returns a single dimensional array that includes all of the decision variables in our model. So now this is a single dimensional array, all vars, that includes all of the decision variables in our model. So now I'm looping over all of decision variables in our model. So this current var is iterating over all the variables in our linear programming model. And when we have a Gurobi variable, there are two fields in it. A Gurobi variable has two fields in it, var name and x. Var name field returns the name of the variable, and x returns the value of that variable. Okay, so now we learned three new things here. A Gurobi model .getVars returns an array that includes all the decision variables in our model. And a Gurobi variable has two fields, var name and x. Let's make a note of those. So if I have a Gurobi model and say getVars, this returns a one-dimensional array that includes all of the decision variables in our model. So then we can iterate over the array to access all of our decision variables one by one. And if I have a Gurobi variable, Gurobi decision variable, and if I look at the var name field, that returns the name of the variable. And if I have a Gurobi variable, if I look at the x field, that returns the value of this decision variable. Good. So let's run this piece of code. Okay. So far is a screen dump when we solve our linear program using the Gurobi. And this stuff that we see over here is what we printed. What did we print? We printed the optimal objective value, which is 20. And then we printed the optimal solution by looping over all of our decision variables. So now what is it? X01 is equal to 1. What else? X12 is equal to 1. X20 is equal to 1. That is the optimal solution, right? X01 is equal to 1. X12 is equal to 1. X20 is equal to 1. So what is the optimal solution then? Let's see. The optimal solution is x01 is equal to 1, so technician 0 is going to job 1. Technician 0 is going to job 1 right over here. What else? x12 is equal to 1. Technician 1 is going to job 2. And x20 is equal to 1. Technician 2 is going to job 0. So this is the optimal solution. Good. Okay. So then this is now how we create a linear program within Python by using loops to create all of our decision variables, all of our constraints. And it's an important idea because when you write a linear program and you solve a linear program in practical applications, you're going to have hundreds of, maybe thousands, maybe hundreds of thousands of constraints and maybe hundreds of thousands of decision variables. So it's impossible to create all these decision variables line by line by line, one by one. So you're going to have to create these decision variables and constraints, all of them in a loop. So it's important to get a grasp of these ideas. Well, okay. Let's say one last thing as we wrap this up. When we were printing the optimal solution to our problem, to our linear programming model, we said my model.getVars that returned a one-dimensional array. We said my model.getVars that returned a one-dimensional array that included all the decision variables in our model. And then we looped over all of our decision variables. We looped over all that array. And then we printed name of the variable and the value of the variable. Okay, good. But there's also another way that we could have accessed the optimal values of our decision variables, and that would be through this xvars array. Because this xvars array also includes a reference to all the decision variables that we constructed. But now remember that this xvars array is a two-dimensional array. So if you would like to access the values of our decision variables, we could have used the xvars array as well. But again, xvars array is a two-dimensional array. So let's do that as well. Optimal solution accessed through the xvars array is. So let's also do that. Now here's what we're going to do for I in range number of x, for j in range number of x. Okay. Now what are we going to do? So let's say print, or let's say current var xvars ijth entry. So now we can print current vars var name and let's also print current vars value. and the current var's value is a number. Let's turn it into a string. Okay. So that would be another way to access the values of our decision variables through this X vars array. So let's run this code and let's see what it does. Example.py, run. Good. So now we're dumping the values of the X decision variables through the X vars array. We're getting the same values. Okay. So they're getting us the same result. They're giving us the same numbers. But in practice, I usually like this approach better because I know that when I'm looping over I for all the technicians and J up, this would be for all the jobs, I apologize, but since the numbers are equal, it doesn't matter. This should be number of jobs. Good. So when I'm looping over I over all technician, J over all jobs, I know that I'm going to refer the Xij decision variable. So when I access the optimal solution through this loop, when I'm looping over I over all technicians, J over all jobs, I know that I'm referring to the Xij variable. Whereas over here, when I'm looping over all my decision variables in a single dimensional array, I don't know what the decision variable I'm going to hit next. That is only hidden in the valid name of that decision variable. Okay. So now if I use this loop, when I is a certain value and J is a certain value, then I know that I'm accessing the X variable for that IJ pair. So this way of accessing the values of my decision variables, I think is a lot more useful in practice. Here, when I loop over all my decision variables in a one-dimensional array, I don't know what next decision variable I'm going to hit. Okay, good. So now we can stop here. The stuff that we learned in this lecture is useful because, again, when we create and solve linear programs in practice through Gurobi, we're going to be dealing with hundreds of thousands of decision variables and thousands of thousands of constraints. So it's important to be able to construct our linear programs, construct the decision variables and constraints through loops. Okay, and that's what we learned today. Let's stop here. It's a good stopping point.